Antarctica and wants to join the society. So we encourage you to join to be a part of these events and get on the and be involved in them. So this evening we've got James Renwick, who's going to tell us about sea ice changes and how things are changing in Antarctica. He's done some very, very interesting research on that. So James, I'll hand it over to you.
Okay, well, thanks very much, Ken. Yeah, so I've had an interest in Antarctic sea ice for 20 odd years now, and yeah, I find it a fascinating topic. So great to be able to talk about one of my favourite subjects this evening. So I guess we'll get straight into it. I'll just do a screen share. See if I can do this right. Get the PowerPoint going. Okay, and all right, so there we go. So hopefully everyone can see that. So yeah, the topic of the talk this evening, Antarctic sea ice, trends and variability. And I guess trends, or the lack of them, has been a big topic of interest for a long time now. And the contrast between what's happening around the Antarctic coast and what's happening in the Arctic couldn't be more different, really. So I'll start off just by talking about the general setting, the seasonal cycle, and just, you know, what typically goes on with Antarctic sea ice on a seasonal and annual basis. Then get on to year-to-year variability around that and what the trends in sea ice have looked like. And then talk about, this is really my interest, how the atmospheric circulation interacts with sea ice concentration around Antarctica on all sorts of timescales. And I'll talk about the kind of day-to-day, week-to-week, through to seasonal effects, and then on to the kind of trend or decadal timescale. And I'll finish off with a bit of an outlook for the future, or maybe it's better to say a lack of outlook for the future. So just to begin, and again, coming from an atmospheric point of view, starting off with a view of the Southern Hemisphere with the winds near the surface of the Earth shown here in this map of the Southern Hemisphere. So we can see Antarctica over the South Pole, and then there's a lack of land between about 65 south and 50 south. And as we all know, I guess it's the one region on the Earth where the ocean currents can flow unimpeded. So we have the Antarctic circumpolar current going right around the globe. And we have the westerly winds blowing around the hemisphere, essentially unimpeded, apart from a bit of the Andes in South America, and to a smaller extent, the South Island of New Zealand. So the westerlies blow pretty much all year round. The north-south temperature difference determines how strong the winds are, and because Antarctica has a very large ice sheet on it, it stays very cold all year round. So the north-south temperature gradient stays pretty strong all year round, and we have strong westerlies right through the year, which is a bit of a difference from the Arctic, where in the summer the northern latitudes warm up a lot and the westerlies weaken off dramatically. That's one of the main differences between the north and the south. So we have these strong westerlies, and then the colours on this graphic show where the storms occur, and the darker the colour, the more storms. So we have a very vigorous storm track over the southern oceans that aligns with the location of the strongest westerlies. I mean, that makes sense from an atmospheric dynamical point of view, and the westerlies and the storms go together in all sorts of ways, and I'll talk about that again a bit later. So we have this situation where the sea ice has to grow out from the coast of Antarctica towards the equator. And you might expect that, given these vigorous westerlies and the very turbulent ocean underneath, that you'd get a pretty bland-looking sea ice field that would extend out from the coast of Antarctica, and maybe it would be kind of circular, you know, to get sheared off at 60 south or something by these strong winds, and you just have a ring of sea ice around the continent. And that's actually not, well, to a certain extent it is what happens, but it isn't. That isn't the story, really. And it's interesting that we don't just have a circular looking or a concentric ring of sea ice around the continent. One thing to notice is that the the coast of Antarctica on in the Western Hemisphere, that is the West Antarctica and across the South Atlantic, the coast is much closer to the pole. It's average latitude of somewhere between 70 and 75 degrees south, whereas on the eastern side, in the Eastern Hemisphere, the Indian Ocean side, the coast of Antarctica is closer to 65 south. So the sea ice effectively has less room to grow on the Indian Ocean side, and this is what we see, that there's a much narrower region of sea ice in the Eastern Hemisphere than there is in the Western Hemisphere. And yeah, I'll talk a little more about some of the consequences of this a bit later on, but I thought I'd start off talking about the seasonal cycle of sea ice. So how does the sea ice grow? Where does it grow? And how does that vary, basically? So here's a map of, or series of maps of the monthly average sea ice extent around Antarctica. And on this graphic, I realise maybe the choice of colour shading is not ideal. The redder the colours, the more sea ice. It probably should have been the other way around, whereas the bluer, the more sea ice. And I think I've done that on later plots, but it does show the extent pretty clearly. And just to explain what's going on here, these graphics come from a collation of satellite estimates of sea ice concentration. So since the late 1970s, the reliable record starts in 1979, so just over 40 years ago now. We have these satellite-based views of, well, the whole globe, but the southern oceans, and the microwave instruments can basically see down to the surface pretty much all the time. And given the altitude of the satellite and its characteristics, we get these pixels or, grid boxes of estimates of where the sea ice is on roughly a 25 by 25 kilometre scale for these low resolution satellites that have been running for a number of decades. So what I'm showing here is the output of those satellite records. So we've got about 40 years of record that have gone into these estimates, and they're relatively coarse scale for people who are used to actually going to Antarctica and looking at the ice close up. It's studied on much finer scales down to a few meters, but these records are on the order of a 25 kilometre scale. So what we see is that there's a massive seasonal cycle in sea ice. It's quite different to the Arctic. In the summer, the minimums in February, most of the ice has melted, and there's a good region in the Weddell Sea just east of the Antarctic Peninsula and along the West Antarctic coast particularly, but otherwise the sea ice is gone. And the numbers in the top right of each of these boxes is the average extent in millions of square kilometres, so just over 4 million square kilometres in February. And then as you go into the winter, the sea ice grows dramatically, especially across the South Pacific and the South Atlantic. As I was explaining before, where the Antarctic coast is closer to the pole, you get a much larger extent of sea ice. So you do kind of get a circular region, sort of extending to about 60 south, which is the latitude circle shown on these plots. But it's not quite that simple. We see a very large extent across the South Atlantic, the Weddell Sea, and across the West Antarctic and out north of the Ross Sea region. But it's quite a narrow band of sea ice, especially across the region over the Eastern Indian Ocean from about 90 east and around south of Australia. And there's some interesting features to the average extent by month. If you look at September, which is the month of the peak sea ice extent, where we've got over 19 million square kilometres of sea ice, so a factor of nearly 5 greater than the minimum in February. There are some interesting bumps and kinks in the distribution. So just east of the Greenwich Meridian in the sort of top part of the plot there, you've got that sort of step in the sea ice edge down towards 60 south. And then over the Central Pacific, there's kind of an elbow or a corner in the sea ice extent where it extends up to about 60 south at about 150 west, but it's much further south on either side of that. And it turns out that these bends in the edge of the sea ice are related to the location of the Antarctic circumpolar current in the ocean. And that location is related to the seafloor bathymetry, basically the shape of the seafloor, the edge of the continental shelf and so on. And a lot of the flow in the ocean on average is quite what's known as barotropic. It's the same from the bottom of the ocean right to the surface. So we're actually seeing an expression of what the seafloor looks like in the edge of the sea ice in wintertime. At this time of year, this week, next week, is about the average timing of the maximum in sea ice extent around the Antarctic. And then it all melts away again over the spring and into the summer. And it represents one of the biggest, or the biggest seasonal signal in the whole of the climate system, this massive growth of sea ice in the winter and then the melt in spring and summer. So it roughly doubles the effective size in terms of the radiative effects, the reflection of sunlight and so on, of the size of Antarctica. That 19 million square kilometres of ice in September is comparable with the aerial extent of the Antarctic continent itself. So it's pretty remarkable that we see this every year, and we see it incredibly regularly. We do have this very turbulent atmosphere and ocean that it has to grow out above or below, depending on what you're talking about. And that changes from month to month and year to year. But it's a very regular progression, and we see that shape in September reproduced pretty much exactly every year. It's quite incredible. So if you just add up the amount of sea ice, and the way this is done with the satellite information, you've got these boxes of 25 kilometres on the side, and what the convention is, if more than 15% of that box is considered to be covered in ice, then that's a sea ice grid point. So the way it's done is you add up the number of those boxes and the area to work out how much sea ice there is around the continent. But the boxes themselves, they have a fraction of sea ice coverage. This is a so-called sea ice concentration, and that ranges from 0 to 1 or 0 to 100%. What's done for calculating the aerial extent is you just add up all of the numbers of greater than 15% of 0.15, and this is what you get. So you've got that minimum of 4 point something million square kilometres in early February, and the maximum of 19 or 18 point something million square kilometres about now in the first half of September. And the dashed lines on this plot show the variability around that average, and the lines are pretty tightly packed, so the variability from one year to the next is very, very small. It's quite remarkable. Like I was saying before, we get this growth in the sea ice reproduced almost from scratch every year to almost the same aerial extent and the same shape, the same distribution, just about every year. So here's a typical example. This is from 2008, 2009. No magic about this, just years that I chose effectively at random. So you can see the 4th of September 2008 on the left. This is the extent on that day from the satellites. You can see the bends and kinks in the distribution there. And February of 2009, a few months later with the minimum, we can see this Weddell Sea is mostly covered, especially the western region and parts of the West Antarctic coast and just off the Victoria Land coast further west. But otherwise the ice is essentially all melted away. And what's happening right at the moment, this is the latest graphic from the National Snow and Ice Data Center in Boulder, Colorado. And it's really amazing to me. Maybe it just indicates I'm an old guy. You know, I still find it incredible that I can click a mouse on a web page and get a picture of what's happening around Antarctica, around the whole hemisphere, just a day or two ago. It's wonderful to have real-time access to this kind of data set. So what we see here is the orangey line is the average edge of the sea ice for the 7th of September, and the shading shows the sea ice concentration. This is what fraction of these little grid boxes is covered in sea ice. And when you add it up, sea ice extent this year is very close to the overall average, but it's not average everywhere. There's a bit of a lack across the West Antarctic coast, north of the Amundsen Sea, and also Central Indian Ocean, but there's a bit more than average over the Eastern Weddell Sea and so on. And you can see where the line and the actual extent match up or otherwise. So overall, though, the total amount is about the average. And you can see that on this time series plot, which shows the days of the year, essentially. The blue line is the average, the grey lines are the individual years. The black line is last year, and the red line is this year. So the red line, you can see, was pretty close to the average, or maybe slightly below for most of this year. And it just crept above the average just in the last couple of weeks. And it's just hovering 10,000 square kilometres or so above the average at the moment. So for all intents and purposes, Antarctic sea ice is right on the average in total this year. And, well, we'll see what happens over the next few months, but it's been close to average for a good part of this year, and there's no reason to suppose that it won't carry on that way through the rest of the year and into the summer minimum period. All right, so that's the seasonal cycle, which I would say is not as well understood as it could be. The timing of the minimum and the maximum, and all the reasons for the shape of the sea ice area. I don't know that we really understand all of those. I think there's stuff to learn from looking at that a little bit more. But getting on to interannual variability and the trends, this is what I think has interested a lot of people. And what I show here is a graphic from 6 years ago now, year by year differences from average in sea ice in September. And then on the right is a plot of trends in sea ice concentration from 1979 to 2014. So the plot on the left, which comes from the NOAA State of the Climate Report group in the US, shows difference from average, which is the 1981 to 2010 average, which was just under 19 million square kilometres. The percentage difference from that year by year for September. And you can see, you know, there's a trend, right? There was a statistically significant upward trend that had been established by 2014. So back in the mid-1980s, the average extent was a few percent below that normal. And by 2013-14, it was 4 or 5% above. So you could draw a straight line through these data and find a significant upward trend, which was the cause of a lot of angst, I would say, in the community. You know, how could this be happening in a warming world? What's going on here? Is it all sorts of things were proposed? There's a few acronyms at the bottom there. Was it the melt of water off the ice sheets, the ice shelves? Was fresh water being put into the Southern Ocean that both easier to freeze than seawater and also relatively cold? So is that causing there to be more ice forming more easily, maybe? Were the westerlies stronger, the Southern Annular Mode? I'll talk about that in a bit. Was there some role of El Nino, the ENSO cycle? Was it the ozone hole? There were all sorts of things proposed for why we might be having this trend. And actually, I got a bit of funding. I put a proposal in 2014, and the overall message there was, or the sort of bottom line of the proposal was, well, why is sea ice extending? And why is it growing? And, you know, give me some money and I'll find out. And part of the story is this plot on the right-hand side. It wasn't growing everywhere. The blue regions now are where the ice is becoming more extensive. So you can see that across the Ross Sea region, or all the way from about 90 east round to the Central Pacific. But near the peninsula, the ice was actually disappearing, was decreasing, and across a lot of the Weddell Sea out towards the edge of the ice, it was also disappearing. So it was quite a complicated picture when you looked at the different regions of Antarctica. It wasn't just that the ice was getting more extensive everywhere. So understanding that was important, as well as just understanding the overall upward trend in sea ice concentration, or sea ice extent, I should say. So, yeah, I got this funding to explain why we were going to see this increase in sea ice. And then as soon as that happened, well, the sea ice stopped becoming more extensive. And if you extend that graph I had before up to last year, September, what you see is that 2014 was the peak. It was about 7% more than normal, and then 2015 was about 0.2% below normal, and every year since has been below normal. This year, like I just showed, is probably going to come in at about the normal. So that period of 6 years up to 2014 of more extensive sea ice seems to have gone away. And when you look at the trends from 1979 to 2019 now, on the right-hand side there, it's the same pattern, but it's mostly the same years, but the colours are softer, so the overall magnitude of the trends has decreased. So things appear to have changed lately, or something's going on to cause these trends to move around. And actually, when you look at the plot on the left-hand side, and you think about the numbers here, the vertical scale is the extent anomalies in percent. That is, what percentage of this 1981 to 2010 average is there more or less from year to year. And the numbers are small, right? They're 2% above, 2% below, and even that peak in 2014 was only 7% above the average. And in the last couple of years, it's been 2 or 3% below. So we're not talking about big numbers, actually. And when you look at the Arctic, where the sea ice in the end of summer, which is also September right now, has been going down dramatically, we're talking about changes of 30 or 40 or 50%, not 3 or 4 or 5. It's like a factor of 10 bigger in the Arctic. So the changes there are way more dramatic than in the Antarctic, but still really interesting to understand. And that's what a lot of people have put effort into trying to understand over the last 10 years especially. So we'll just look through some of that now. So starting to break it down then, looking at individual months or different parts of the seasonal cycle. So what I've got here is, again, from 1979 to 2019, the trends in sea ice concentration, and this is in percent per decade. So 15 would be 15% more or less sea ice over 10 years in a given grid box. So we've got February, June, September and December, which is roughly the minimum sort of growth period, the maximum, and then the melt period in the bottom right. And there are different trends at different times of year. So in February, at the time of the minimum, there's been a lot of loss of sea ice along the West Antarctic coast and west of the peninsula, while it's been growing east of the peninsula. September, which has got a lot of the attention because it's the time of the maximum, there has been growth in sea ice out near the edge of the ice field across the eastern Indian Ocean and across a lot of the Pacific, but there's been loss of ice, or decrease in the concentration, I should say, closer to the coast across the Pacific and across a lot of the South Atlantic and so on. So, you know, again, quite complex picture and quite a lot to explain in these plots. But not only is it different from one part of the seasonal cycle to the next, this pattern of trend has also changed in time through the decades, and this is why we see these strange ups and downs in the total extent from one year to the next. So we've got roughly 40 years, we've got 41 years of record here. If we just split it up into the first half and the second half and draw these pictures again, you see some quite striking differences. So if we look at the first 20 years from 1979 to 1999, this is what you get. Same colour scale, as the colours are generally darker because over a shorter period you see much more distinct effects. So if we just concentrate on September, let's say, you see very strong increase in the sea ice out near the edge of the ice field from 120 east or so, sort of south of Australia, right across to the Central Pacific, but a decrease in the ice, broadly speaking, further east from that and across the South Atlantic. Also very strong growth on the ice field across the South Pacific, south of New Zealand, south and east of the Ross Sea, in December at the time when the ice is decreasing, so that would suggest it was decreasing more slowly, melting more slowly. And in February, when the ice is at its minimum, you have very strong decreases on the amount of ice just west of the Antarctic Peninsula and so on. And then if you look at the second 20-year period, so from 2000 to 2019, you see some big changes. So here's 79 to 99, and then 2000 to 2019. And across the South Pacific, especially in September, in the first 20 years, we had this big growth in the ice south of New Zealand, basically. And in the most recent 20 years, there's been a decrease, if anything, a decrease in the amount of sea ice south of New Zealand, and a big increase near the Antarctic Peninsula. So virtually the opposite pattern to what we saw in the first 20 years. And I'm not going to go through all the bits and pieces of these plots, we'd be here all night, but there are some big changes and often some major reversals in the trends between the last part of the 20th century and the first part of the 21st century. So when you look at the whole 40-year period, that's why you see somewhat more muted trends. And I think there's been a realisation over the last, 20 years or so, especially the last decade, really, that a lot of what's going on here is it's not really a trend. It's just the response of the sea ice field to atmospheric variability, the way the winds have been blowing. There have been some interesting trends or longer-term variations in the atmospheric circulation, and they've, affected the ice field in certain ways. But it's not as though we're seeing a wholesale change in the sea ice behaviour like we're seeing in the Arctic, where the extent has decreased somewhere between 40 and 50% in the late summer and September. So it's a much more dynamic story around Antarctica, and the atmospheric circulation plays a much more dominant role, which is where I got interested in this whole story. So I thought I'd just go through some of the results we've come up with looking at how the winds connect to the sea ice field on different timescales. So starting off with a sort of daily to weekly timescale, this graphic here shows again the colours, and it's slightly coarser resolution data. You can see it looks a bit more pixelated, but what you can see, the blue colours are where the ice is increasing, and the red colours are where it's decreasing. This is at the time of the maximum, roughly over the winter, going through to about this time of year. And then the contours are, effectively they're surface pressure. So the solid contours are the high pressure regions, so they're highs, and the dashed contours are low pressure regions, or the lows, the storms. And in the Southern Hemisphere, the winds blow anti-clockwise around the highs and clockwise around the lows. So what you get is between east of the high pressure centre and west of the low pressure centre, you've got flow from the continent towards the equator. So you've got southerly winds, and that's where you see increase in the sea ice. So you've got the cold air flowing north just over the Amundsen Sea region there, and warm air flowing south over the Weddell Sea. And this is not, for this analysis, we took away all of the longer term trends. This is just the daily to weekly variability. So what we see here is on a daily to weekly timescale, the location of the highs and lows really dominates where the ice is growing or decaying. And what you see on this plot is what's known as a zonal wave number 3. So there's 3 high pressure regions and 3 low pressure regions, and these 2 plots they go together. So the 2 of them, one tends to follow the other, and it's basically showing the same pattern, but it's just shifted around towards the east a bit. So these highs and lows migrate eastwards around Antarctica, and as they go, they bring in increases in the sea ice field to the east of the high centre, decreases to the east of the low centre, and so on. And these are some of the most dominant patterns in the variability of the sea ice on this kind of weekly timescale. So that's telling us that the meridional part of the wind, the northerly, southerly part of it's blowing northwards, you've probably got more sea ice. Blowing southwards, you've probably got less. That's a pretty big part of the story. If you look closely, you'll see that it doesn't work all the time, everywhere. And I'm making this story a wee bit simplistic, but by and large, it does work over a lot of the Antarctic sea ice region. I guess there are two things going on here. One is that the wind just pushes the ice. So where you've got the flow off the continent, probably the katabatic winds flowing off the ice sheet are a bit stronger, and you've basically got wind pushing the ice away from the continent. So you can generate more sea ice through Polynya action, or just generally from the ice thinning near the coast, so it can grow more and grow further equatorwards, and on the regions where the flow's towards the coast, the ice is being shoved up against the coast and shoved away from the open ocean, so you get a decrease there. So that's one part of the story, and then the other main part is just the heat flux. So when you've got flow from lower latitudes towards the continent, you've got warmer air being sent southwards, and that's going to melt the ice because it's warmer. Ditto when the air is cold and flowing off the continent towards the north, you're making conditions colder, so you're making it easier for the ice to form. So both of those effects definitely play a role, but the relative importance of each of those varies around the Antarctic coast, and varies with the time of year, actually, it turns out. And if you look on a sort of closer to monthly time scale, and I apologise a bit for this plot, it's not quite so obvious what's going on. It's from a different paper, and it wasn't drawn with the circulation and the sea ice on the same plot, so you've got to kind of look between the top and the bottom. But this is looking at roughly the monthly time scale, and again the year-to-year variations have been taken out of this, so it's just what happens on that kind of monthly time scale. And what you see again is this sort of sequence of highs and lows, and relative increases and decreases in the sea ice. So what's shown on this top plot, this is the atmospheric circulation. Think of it as the surface pressure field. But here the red contours are the highs, and the blue contours are the lows. So we've got anti-clockwise circulation around that big high over the southeast Pacific. And in the sea ice field below there, this time, unfortunately, the blue contours mean a decrease in the sea ice, and the red contours mean an increase. So in the region where the flow in the atmosphere is towards the Antarctic coast, that's just west of the high pressure region, we've got a decrease in the sea ice over that region just north of the Ross Sea. And near the peninsula, we've got southerly flow between the high and the low, and we've got an increase in the sea ice. And these two, this atmosphere and the sea ice pattern, go together on that monthly timescale. It's the most prominent signal in the data set over this 35, 40-year period. And it doesn't say it on this slide, but there's an interesting time lag that comes up in this analysis, that there's roughly, it's nearly a week time lag between that atmospheric pattern setting up and the sea ice response. So you get this sequence of highs and lows, which is often generated just randomly in the circulation of the atmosphere. We get this sort of wave pattern that develops, bends in the storm tracks and the westerlies, basically. They can be triggered from the tropics. An El Nino event can cause this kind of wave pattern to occur over the South Pacific, but we don't need an El Nino event, it just happens naturally anyway. So you get this flow of air with northerlies flowing towards the Ross Sea and the southerlies flowing off the peninsula region. And a few days later, you start to see this pattern in the sea ice, where the sea ice is decreasing over the Central Pacific and it's increasing near the peninsula. And that is just an expression of the natural variations in the atmospheric circulation on this kind of monthly 3, 4, 5, 6 week kind of time scale. So it's a very similar pattern to what we saw on the daily to weekly time scale. It's also a pretty similar form to what we see on the seasonal time scale. And it turns out, I've got it written on the slide there, that recent work confirms this for the trend pattern. So you see this kind of thing even on the 10, 20, 30-year time scale. The average location of the highs and lows, or what the winds are doing around Antarctica, does imprint very strongly on the average extent of the sea ice, and this appears to explain a lot of what goes on in the atmospheric circulation and in the sea ice field over the last several decades. So just to go to the seasonal timescale from an earlier paper, this time I've managed to plot the circulation on top of the sea ice extent, or not actually the sea ice extent, it's the latitude of the edge of the sea ice. This plot's a bit exaggerated so you can see what's going on. The blue region there across the Central Pacific, it's a factor of about 5, I think. The sea ice doesn't extend that far north, but it does extend further north than average. And it extends, it's closer to the Antarctic coast near the peninsula. And this is when you've got this pattern with a deeper low, that's the blue contours over the southeast Pacific. So again, we've got flow from the south in the regions where the ice is extending, and flow from the north in the regions where the ice is decreasing. And this analysis actually took account of all the year-to-year variability, and it's very clear that El Nino events are a big player in this. That when you have an El Nino event or a La Nina event, when you get these big oscillations in the tropics, they tend to trigger big wave trains that flow across the South Pacific. So actually in a La Nina, you get the pattern that's shown here, a high region, higher pressures just east of New Zealand, big low over the Southeast Pacific, and then a follow-on high over the South Atlantic. So during a La Nina, you expect to see more sea ice over the Central Pacific and less sea ice near the peninsula. And vice versa, in an El Nino, you get less sea ice over the Central Pacific, and so on. So it turns out that on the 20-year, 30-year timescale, it's the sequence of El Ninos and La Ninas that actually dictate how much sea ice you get around the Antarctic coast, at least across the West Antarctic. So all of this has been really about the West Antarctic. And that's because the El Nino influence is felt, it happens in the Pacific, and so it's felt over the Pacific more than it is felt elsewhere. So it works well across the West Antarctic region, the Pacific region, and the decadal, the sort of 20, 30-year variations in the El Nino cycle actually turn out to be really important for what's happening with the Antarctic sea ice. There are analogous things that happen around the rest of the Antarctic coast. There's less sea ice to play with around the Indian Ocean side, but there are influences there. And the Indian Ocean dipole, which is a similar kind of oscillation in sea temperatures in the tropical Indian Ocean compared to the ENSO cycle, that appears to have some influence on sea ice around the Indian Ocean side. And yeah, actually a PhD student of mine, Florence Isaacs, has been working on this for her PhD, and she shows that actually, yeah, there's some quite significant relationships between tropical variability and sea ice around the Indian Ocean side or the East Antarctic coast. It's less dramatic, you might say, in some ways than the West Antarctic, but definitely still there. So tropical variations do affect the sea ice extent around the whole of the Antarctic coast. So I wanted to just have a quick detour into some of these atmospheric patterns just to explain what's going on. So just to jump to the El Nino story, or in fact the Pacific decadal oscillation, which is a feature of the global oceans, really, the Pacific Ocean certainly, that modulates the El Nino-La Nina cycle. So what happens is this map here is a map of sea temperature difference from normal, averaged over 20 years or so. So what we see for a 20 or 30 year period is relative warming of the sea ice over the eastern Pacific, centered on the equator. So that's that reddish region lying along the equator there and up the west coast of North America. And at the same time, you see lower than average sea temperatures over the central North Pacific, and somewhat lower than normal temperatures over the New Zealand region and out into the central South Pacific, along about 30 south. So when this PDO feature looks like this, when it's positive, so-called, where it's warm in the Eastern Pacific, it becomes easier for El Nino events to occur. So when you have this positive PDO, you tend to get more El Nino events, and they have certain effects on the wave patterns across the South Pacific and certain effects on the sea ice. And then this whole thing flips over and it becomes cooler in the equatorial Pacific, and it becomes warmer east of Japan and around New Zealand. That's the negative PDO. And in that phase, it's easier to get La Nina events. So you can have quite opposite influences on what happens to the sea ice across the West Antarctic. And when you look at the variations in the Pacific decadal oscillation thing, this is a plot of the index of the PDO. So it's basically how much does the sea temperature field actually look like, this pattern. When it's very positive, it looks a lot like this. When it's very negative, it looks like the opposite. It's cold off the coast of South America and it's warm east of Japan and so on. So what we see is, from year to year, it's relatively noisy, but if you smooth those numbers and look at the longer term variations, what you see is this is why it's called a decadal oscillation. You see quite long periods of almost all negative values and quite long periods of positive values. And if you look at the timing, what we see is from the late 1940s until the late 1970s, we were in a negative PDO period. And the last 20 odd years of the 20th century were positive PDO. And then since the turn of this century, it's been mostly negative, although it's sort of jumped around quite a bit. So what we've got is we had a La Nina dominated period back in the sort of middle part of the 20th century, then an El Nino dominated period in the last 20 odd years of last century. And in the last 20 years or so, it's been sort of a mix of La Nina conditions or not a lot going on with this oscillation in the Pacific. And it just turns out that when you look at the data set, the satellite record of sea ice around Antarctica, that started in 1979. So the first half of that data set occurred during this positive PDO period where we had mostly El Ninos, and the second half of the data set has occurred during mostly the negative phase of the PDO. And this is just purely an accident. It wasn't done by design. So you might expect to see different things happening with the sea ice around Antarctica in these two different periods, and that is exactly what you do see. The other thing I wanted to mention was the Southern Annular Mode, which is what controls the westerlies over the Southern Ocean. So we have this is the plot I showed before of the westerly winds and the storms. That's the colours, the number of storms. And this is the average pattern. We have the westerlies blowing around the Antarctic coast. But on a sort of weekly to monthly timescale, this whole system concertinas in and out. So the westerlies and the storms move towards Antarctica for a few weeks and the winds get stronger. That's what's known as the positive phase of the Southern Annular Mode, the SAM. And then the whole thing moves out towards the equator, and the westerlies on average get a bit weaker but extend much further north, and so do the storms. So when New Zealand's under that influence, it's quite windy and stormy here. But over the southern oceans, the westerlies actually weaken off, and that can have quite big influence on what happens to the sea ice, certainly around the edge of the ice field. And one interesting thing about the SAM is that it's exhibited a trend over the last 40 or 50 years. So what we've seen on the left, a graphic of another way of looking at the SAM is the pressure field. So the blue contours are low pressures, the red contours are high pressures. So the positive SAM, you've got lower pressures over Antarctica and higher pressures over the New Zealand region, stronger westerlies over the Southern Ocean. And we've seen, the SAM thing on the right there, it jumps around a lot. But over time, there's been a predominance of the positive SAM, that is stronger westerlies over the Southern Ocean, stronger, deeper Amundsen Sea low, and so on. And that's actually been driven by the ozone hole, which has caused the atmosphere over Antarctica to cool down, especially in the spring and summer, strengthen the north-south temperature difference, strengthen the westerlies. And climate change is a small player in this, but important. So greenhouse gas increase has led to the atmosphere warming faster in the tropics than it does over the pole. So again, the north-south temperature difference has increased, leading to stronger westerlies over the southern oceans. So that has been a player in what's been happening with the trends in sea ice. So just putting that together then for these this 40-year period or the two 20-year periods, going back to those graphics I showed before. Here's the trends in sea ice for the first 20 years, the positive PDO period. And when you overlay the trends in the circulation, you see some quite striking things. And just concentrating on that September graphic there, here the dashed lines are the lows and the solid lines are the highs. So we've got a low centre over the central South Pacific at about 60 south. Normally pressures are low closer to the peninsula, the Amundsen Sea low, but pressures were a bit higher than average there, or trending upwards over that 20-year period. So we had flow towards the pole east of that low centre, so that's where we see the sea ice decreasing, and flow away from the Antarctic continent towards the north over that broad region where the sea ice was growing through that 20-year period from the central Pacific around to the sort of eastern Indian Ocean region. So quite strong evidence, and again, I won't go through all the months and all the details, but you can see regions where you might expect there to be warm air flowing southwards where the ice is decreased, and cold air flowing northwards where it's increased. And then you look at the most recent 20-year period, and the trends in the circulation are quite different. In September, again, we see a decrease in pressures over Antarctica and an increase in the middle latitudes. That's the signature of the Southern Annular Mode, so stronger westerlies everywhere, but a deeper Amundsen Sea low. So, it gets complicated, but generally speaking, that has contributed to an increase in the sea ice near the peninsula and a decrease in the sea ice further west. So again, it's not a perfect story, but you can marry up changes in the circulation with changes on the sea ice, even on this sort of 20-year kind of timescale. Okay, so that's a long story about how the atmosphere affects the sea ice field, and there's an amazing amount of mileage you can get out of that. It really is a dominant feature of what happens to the sea ice. But what else is going on? What haven't I talked about? Well, the sea ice, it's frozen seawater, so what the ocean does must be important. So what about the fact that the ocean's warming? Well, that's a really good question, I think. Sea surface temperatures, if anything, have decreased a bit around the southern oceans off the Antarctic coast, but there is warming at depth, so there's warmer water upwelling more, and it may well be that will start to dominate the story in the next decade or two. What about the fact that air temperatures are increasing? That should be having an effect, and probably around the northern edge of the sea ice field, we might expect to see the extent of sea ice starting to be chipped away at. What about this input of fresh water from the ice sheets and the ice shelves? Probably an influence. There's a lot of work going on at the moment to try and understand that, but right now it's a bit of a coin toss as to whether you might expect that to be helping the ice to grow or not. And again, it depends on just whereabouts you are around the Antarctic coast. The katabatic winds that flow off the ice sheets that are big players in the growth of sea ice around especially in the Polynya regions. There's very cold winds blowing off the continent, and you really get rapid growth of sea ice when the katabatics are strong, and not so much when they're weak. And has the increase in the westerlies driven a change in the katabatics? Good question. So, what does the future hold for sea ice? I would say it's pretty hard to say. We've got to think about all of these different influences. So if you look at atmospheric effects on the sea ice, well, the ozone hole is actually filling in now, so that should decrease the north-south temperature gradient, which should be a negative influence on the Southern Annular Mode, which should cause the westerlies to weaken off a bit. But we've got global warming driving an increase in the north-south temperature difference, so that should drive a positive trend and increase in the westerlies around the Southern Ocean. Then we've got these wave patterns over the top, these sequences of highs and lows that often are driven from the tropics, from El Nino events and so on, and sometimes they just happen naturally. And all of these things, including just the general warming of climate and changes in the ocean circulation, all add up what happens to the sea ice field. So I'd say we have to understand all of these effects before we can really say what sea ice extent is going to do around Antarctica. So just to summarise then, so yeah, there's a lot of variability in sea ice, and I would say there's no real trends at all. There haven't been yet. There's been a few ups and downs, but they're explainable by just what the atmospheric circulation's done. So it's really a function of surface winds, ocean waves driven by the winds are important, heat fluxes are important, and this is all tied back to the trend in the Southern Annular Mode, which is probably changing for the future, decreasing. Also driven by changes in the El Nino cycle and the Pacific decadal oscillation across the Pacific. And exactly how that's going to play out in future is less than obvious. And there are other internal influences. I mentioned the Indian Ocean dipole, zonal wave number 3. There's various other things going on that all actually play a role in sea ice variability. So I think we really need to look a bit harder at how this variability works, even how the seasonal cycle works, and really what are the trends? Are there trends? And if so, what's driving them? And we've got to consider not only the influence of the atmosphere, but also the ocean and the continent itself, what's happening with meltwater into the Southern Ocean. So I'd say sea ice extent is at the mercy of the winds, but the warming climate is going to have an effect sooner or later. The ice can't keep growing, and it's probably can't even maintain itself at its present extent as things warm up. So I really wonder whether, is total sea ice extent now on the decline? Have we seen the peak and now it's just going to go down? Or could we get another 2014 happening in the next few years? I think that's possible, but it's becoming less likely as time goes on. So that was the presentation. So I'll stop sharing, and if there's a few questions, I'd be very happy to take them.
That was really interesting. Thanks, James. Given just the sheer volume of ice, I would never expect atmospheric conditions to have that much of an influence on them. So that was right. It's a whole new learning experience. I don't see any questions on the chat feed, and my problem is, as I wrote down a question, you answered it in the presentation. So
oh yeah,
you've preempted all that. So on behalf of the Antarctic Society and all the viewers out here, thanks very much for that, and a whole new insight into Antarctica, and how climate change is affecting it, and how it will affect climate change in turn. So,
well, my pleasure, Ken. Yeah, thanks for the invitation.
That's great. Yeah, so we normally would have Linda Kessel, who's the president of the Antarctic Society, who would do an introduction, but she's bumped into some technology problems, and so I'll sort of stand in as president. So the society's is sort of geared for anyone who's interested in all things Antarctica. It's not necessarily science; it's the sort of political side, the natural history side. Just so if you're interested in anything Antarctican, please take a look at the Antarctic Society website, and we encourage you to join and be a part of it. So coming up with, as I say, as I said right at the start, this is the fourth of the 5 series, webinar series. So in 3 weeks' time, we've got Judy Lawrence, who's going to tell us about what we need to do to adapt or mitigate the impacts of climate change. So what, it's inevitable. What can we do about it? So I hope you've enjoyed the series so far, and looking forward to seeing you in 3 weeks' time. So thanks very much, everybody.
Okay. Thank you.